Hello, Math 20-1. I hope you're having a wonderful evening. Just a reminder, when you go back to one of the best questions I'd like you to ponder as you're fighting through the previous day's assignment was the multiple choice question and the study notes. I don't always assign them, but they sure are good for reflection. So when you ponder back to the previous section, how was simplifying a radical with a variable expression similar and yet different than simplifying with a numerical radicand? So how is the square root of 12 different than the square root of 12a5b4? So these variable expressions were tricky, and I'm not sure they made 100% sense. So if you were tutoring somebody, how would you see it's different? What's your strategy? And I want to hear from you. So that's something I want you to think about for tomorrow as you try to do your assignment. Okay? So continuing on with our work, you have the checkpoint, which I didn't assign, but in 2.3 we're now going to take what we learned before, and now you can see what's the learner outcome, what's the focus? Well, we're going to simplify sums and differences of radical expressions. Well, how does that work? Well, it turns out it's really similar to expressions like this from Math 10. How do we simplify an expression like this? Do you remember? Please try it and then come back and look and see what Mr. K did. Does it make sense? So I have those expressions simplify. What do you get? So do those getting started questions and then come back and look. Okay? So if you had a chance, okay, now I'm continuing. What you should have got there is minus x minus 2y plus 1. Why? Because these brackets don't really mean anything. It's really 2x minus 3y plus 4 minus 3x plus y minus 3. The brackets aren't really necessary. And if we collect our x's and our y's, and our numerical coefficients, we end up with minus x's, minus 2y, and minus 1. All right, so we need to be aware of what we learned in Math 10, collecting like terms. Remember those words? Well, what about the next one? Ooh, the next one's a little bit trickier because we have that negative there. So again, complete it and then come back and see. When I complete it, I know that if I distribute that negative to all three terms, I get a positive 2x, a minus 3y, and a plus 1. Right, so when I collect my like terms, I get minus 2x's, plus 2y, and plus 3. Okay, what about the next one? Ooh, that red kind of gets in the way there. I was trying to emphasize, but we can see that, well, I need to do the distributive property. So for Math 10, the distributive property, oops, I wanted that to be red. So I've got a 2 and a 2 and a 2 distribute. Now that's a minus 3. So minus 3 to each of those. So be careful. When you distribute that, what do you get? Well, we end up with a 2x plus 4y minus 4 and a minus 3x and a plus 3y and a minus 3. Collect my like terms and I end up with minus x plus 7y and minus 7. Okay? So as we carry on in our travels on the next page, we are supposed to consider what strategies can be used to simplify sums or difference of radicals. So if you remember back to what we were doing, if we had 3x squared and root 7x squared, those are considered like terms, right? It's the variable and the exponent that make it a like term. What are other examples of like terms? Well, obviously 3x and 5x, those are like, and 2y cubed and 4y cubed, those are like terms. So it's the variable and the exponent that make it like terms. Well, what make like radicals? Like radicals are radicals that have the same radicand and index number. So what are like radicals? Well, like 3 root 2 and 5 root 2 and so on. Those are like radicals. And the nice part is that, as you can see in our notes, if they're unlike radicals, you are stuck in the mud. There's nothing you can do with those. If they're like terms, you can collect them, you can add them up, just like 4x and x is 5x. So having like radicals we can work with, and having unlike radicals, you're done, right? 3 root 2 and 3 cube root 2 and 5 square root 2, those are not like radicals. They have a different index number, and we can't work with those. There's nothing we can collect with them, okay? So in the next question, you are asked to simplify the following question. So just because Mr. K needs a little more space, I'm going to do it over here. And in the first question, that's a really nice question. So I want you again to try these questions on your own and then come back and do them as you need. Whoopsie, I didn't want that. So in the first question, question A, I want you to just look at that and go, wow, those are like radicals. 9 root 5 minus 5 root 5. That was easy because they're like radicals. Like radicals, I collect them. Now in the next question, when you have the cube root of 24 minus the cube root of 192 minus the cube root of 375. Now they're all cube roots, but they're not like radicals. They don't have the same radicand. So you're going to need to simplify them. So you get your list of perfect squares out and you realize, okay, sorry, perfect cubes. So what is 24? Well, my perfect cubes, I know. I think that that's 8 times 3. Don't forget the index. So 8 times 3 minus the cube root of 192. Okay, so 8's a cube, 27's a cube. What else? Oh, I know. That's 64 times 3. Perfect cube of 64. Lastly, the cube root of 375. Well, I know that 5 times 5 times 5 is 125. Ooh, that's a good one. 125 times 3. Therefore, these are all my perfect cube, perfect cube, perfect cube. So I'm going to rewrite that as, that's going to be 2 cube root 3 minus, perfect cube was 4 cube root 3 minus 5 cube root of 3. Oh, I have the same radicand and index number. Therefore, I can collect those together, and I get a grand total of minus 7 cube root of 3. Okay, so simplifying radicals and then collecting the like terms. Okay. In question C, again, I think it's time for you to fly and learn. I want you to try this question on your own and then come back and see if Mr. K did it right, So you've tried it, you're back to see if I'm doing it right. And now I go through and I look at my magic chart of perfect squares, and I think this is 9 times 7. That seems good. And 40. What's a perfect square inside of 40? Well, what can I do with that? I think the best I can probably do is 4 times 10. 90. That seems pretty good, but I think the best I can do is 9 times 10. And 28, that's a pretty good number, but I think the best I can do is 4 times 7. I then decide to perfect square, perfect square, perfect square, perfect square. So I take the square root of those. That ends up being 3 square root 7 plus 2 square root 10 minus 3 square root 10 minus 2 square root 7. So I collect my like radicals. I have root 7s and I have root 10s. So I can collect my 7s together and get 1 square root 7 minus 1 square root 10. And that would be my final answer. Okay? Seems pretty reasonable. And you don't really need the ones. They may not have that. Okay? So what do we do now? Oh, well, now we've got variables. And this is where two things happen. You need to remember what we talked about at the very beginning or at the end of last section where simplifying radicals with numerical radicands, that was straightforward. But now we've got radicands with variables. And you need to identify restrictions. And we're going to talk about that next day in class. I've got a whole sheet. Where it mentions this defined, I want you to ignore that for now. If you can figure it out on your own, and you understand, that's great. But I'm going to actually talk about that in depth tomorrow. So for now, just leave that alone. Let's just simplify first, right? So if again, we look at these examples, and you can follow the instructions there if you choose, I am not going to write down absolute values beside them, but we will talk about that, okay? Or maybe okay. Okay, so there's some picky little things with the absolute values that you'll notice, and I don't want us to get too caught up on that really picky nature of that, but I do want us to mention it once in a while, okay? So in the very first question, this should make you smile. Why? Because they're the same radicand and also radical. So therefore, they're like terms. I can simply go 6 plus 5 is 11 root a minus 11 root a. Whoa, everything blows up and you get equals 0. They all blow up, right? 11 root a minus 11 root a, all gone. We don't have to do any work at all, okay? In question B, though, we have the square root of 50 a squared b minus the square root of 8 a squared b. All right? So when I look at this, I go, okay, well, I have to reduce this. So first thing I do is say, well, I know how this works. These are square roots, so perfect square. This is 25 and a 2. A squared is a perfect square. Then I've got 8. That's 4 times 2, and a squared and a b. So when I simplify the square root, I say to myself, well, that's a perfect square, that's a perfect square, that's a perfect square, that's perfect. So what do I get when I do this? I get 5 and a. What's the square root of a squared? Just a. What's left inside is 2. In the next one, square root of 4, whoopsie, I want that to be blue. Square root of 4 is 2. Square root of a squared is a. But what's left inside? I end up with the square root of 2, but I also have a b there. Therefore, these two, oops, was I supposed to have a b in this one too? I was. No wonder they were different. Okay, so there's still a b right there. So now I have 5a minus 2a square root 2b. That's the radicand. So therefore, 5 minus 2, I end up with 3a square root, whoopsie, I wanted that blue, 3a square root 2b. And that would be our answer. Now if you look, technically, we are supposed to have 3 absolute value a square root 2b. Why? Because a can never be negative. And so when you take that square root of the a squared, you can't have plus or minus a. It can just be a positive a. So that when you take it back in, okay? And we can maybe talk more about that as things come up. But I don't want to emphasize that too much, okay? In question C, oops, I'll pause. So again, you guys can give this one a go on your own. You don't really need me, so give it a go, come back, and then try. It's really 2 questions like we did in lesson 2.2, right? So you got a cube root. Oh boy, perfect cubes, right? So I look at this and I simplify. So what is the cube root of 27? Well, the cube root of 27 is a 3. And I also have the cube root, so that's a perfect cube as well. So I've got 3p cube root q. Plus 8, again, the cube root of p cubed, that's just p, so I've got 8p cube root of q. Wait a second, I've got like radicals, so I can collect these terms. 3p plus 8p is 11p cube root q. And all was good in the land. All right? They don't seem so bad, right? When we carry on to example number, it's example number 3, last example, we can see, ooh, they're starting to get a little more involved. They talk about restrictions. But in the very first question, you can see, in the very first question, well, let's go look. In the very first question, we can see, all I really need to do is collect my like terms. They are m's and m's, and they are n's and n. So when I collect the like terms, I just collect. And my like terms become 7 minus 3 is 4 root m. And minus 2 plus 5 is plus 3 root m n. And all was good in the land, right? So all we have to do is collect like terms, okay? Nice. When we look at the next one, we need to be really careful because they're being tricky, right? Again, you can try this on your own and come back. You don't have to just watch me. I could get it wrong, right? So if you look, as you come back, this and this and this, they all look the same. But when you look closely, the radicands, the index numbers are different. 3 and 3 and square root and square root. So they aren't all the same, but we can collect like terms. But in this case, we only collect, right? We got to collect the cube roots and comma the square roots, right? They are like radicals, but they aren't all the same. So therefore, what do I really have here? Well, when I look at the cube roots, I got 2 minus 7. That's minus 7 cube root minus 3b. And then I've got 8 plus 3 is plus 11 square root minus 3b. So that was kind of a tricky one, right? We have to watch that. And the last question, oh boy, we got some simplifying to do again here. So again, we rewrite this using the tricks we've learned. And so we rewrite it with the tricks we've learned. Mr. K had to do a little rework in here, as I forgot one little thing along the way. Anyway, so we work it really with 3 square root 16 and 2, a to the 4th and an a left over, minus 2 square root 9 times 5, b squared and a b, plus 5b square root 25 times 5, and there's a b, minus 2a square root 36 times 2, and an a squared and a. Okay, so now what do we do? Well, perfect square, perfect square, perfect square, perfect square, perfect square, nothing else, perfect square, perfect square. So as we rewrite this, buckos, we end up with 3, and we also have, because of the perfect square, I'm going to just stay with the blue, you guys, 3 with a 4 and an a squared, square root, who's left? 2a, minus 2 and a 3 and a b. On the inside, what's left is 5 and b, plus 5b and a 5. What's left inside is 5b, minus 2a and a 6 and an a, square root, what's left inside? 2a. When we combine and multiply out, simplify, I have 12a squared root 2a. I have minus 6b root 5b plus 25b square root 5b and minus 12a squared root 2a. Do we have like radicals? You bet. This one and this one are root 2a's. They're like. This one and this one are root 5b's. They are like. The bad thing, or I guess the good thing is, these two, the red ones, blow up. There are 0 root 2a's left because minus 12 and plus 12 blow up. So in the end, I've got 25b minus 6b. I've got 19b root 5b. And all was good in the land. Okay, so that's how you complete lesson 2.3. We will see you in class tomorrow when we will dive in, dig deeper, and make sense of all this. Okay, good job. See you tomorrow.